Okay, welcome back to the second part now. So the second part, or third part if you call it the introduction. In the second part of the lecture, we will now be concerning ourselves with vacuum generation, which means we need to look into roughing pumps. So what kind of roughing pumps do we have? We'll go through the most common types and what kind of high vacuum pumps do we have. So the roughing pumps are essentially mechanical pumps where we push molecules and molecules push molecules. So we have some kind of fluid dynamics happening. Whereas with high vacuum pumps, usually we have either just kinetics or we have some kind of sorption that creates the high vacuum and ultra high vacuum. So this is the main difference here. So here we've got some kind of fluid mechanics happening, and here we've got some kind of surface phenomenon happening. And if we go back to the tablet, just to draw again what a fundamental ultra high vacuum system looks like, basic UHV system kind of looks like, you have some kind of chamber that you do your work in. I'll call it measurement chamber, main chamber, whatever. And to that main chamber, you have some kind of gauge, some kind of measurement, some kind of, vacuum gauge. And connected to it, you have a UHV pump, and you also will need some kind of, let's just put it here, you will need to have some kind of roughing pump which some kind of roughing pump, which has the main purpose that it just gets rid of, all the molecules that are in there. So if a lot of the UHV pumps are sorption pumps, so the UHV pumps are usually either sorption pumps or they're differential pumps. Differential sorption means limited capacity. And sorption pumps would be iron getter pumps, non-evaporative getter pumps, titanium sublimation pumps, things like that. And differential pumps differential pumps means that the pressure in the UHV equals some factor, let's say it's some factor C times pressure from the backing pump. And this would be a turbo pump. So in both cases, we need some kind of roughing pump for the UHV pump. In the case of the sorption pump, they have a limited sorption capacity. So we need to get rid of most of the molecules beforehand. Otherwise, we'll just saturate the pump before we get to anything. Or the reaction can be much too strong, like a neck pump, for example, can just start burning. Or a TSP pump. And in the case of differential pumps, the pressure that we can generate in our measurement chamber is essentially proportional to the pressure in the backing pump. Now, to first order, we'll get to why this is not 100% true anymore, but this is roughly why we always need a backing pump. The difference is, of course, for a sorption pump, we need backing only initially. So for the sorption pump, we need the backing only initially, and for a differential pump, we need always backing. We always need backing, because if we switch off the backing pump, we're essentially pumping against the atmosphere, and we will not get to a very good pressure. And so this is why here I've put a valve, because for a sorption pump, you initially rough everything out, and then you just leave everything as is. And then obviously we've got a gauge, but we'll get to the gauges in the next lecture. And so first we'll get to the roughing pumps, okay? And as roughing pumps, I'll only talk about roughing pumps that are really relevant for us in APT. Again, there are some pumps, especially for large-scale industrial applications, that are a little bit different, but that's not really as interesting for us. What's interesting for us is essentially the pumps that we can have, that we use for smaller systems like an atom probe would be. And there we have let's keep the colors. There we can have membrane pumps. We can have rotary vane pumps. We can have scroll pumps, and we can have roots pumps. And the function, the way that a membrane pump works is essentially, as the name suggests, it works via some kind of membrane. So we have a membrane here, and we have some kind of piston at the bottom of the membrane. We've got some kind of piston at the bottom of the membrane that goes up and down. Yeah, so you might have some wheel spinning here that bulges the membrane up and bulges the membrane down. And the membrane is essentially fixed into some kind of casing, and over the casing you have an inlet and an outlet. Obviously the inlet and the outlet, they need to be conforming to whatever shape the membrane has when it is up, but something like this. And here they have an inlet valve and an outlet valve. So you get an in and an out. And you can see this is a very simple mode of operation. So the upside is that they are very simple, which also makes them cheap. And they're pretty silent. So they're not particularly loud. The downside is that the membrane needs maintenance. And roughly, I mean, if you've operated a LEAP, they use membrane pumps. Then you will see that every 2 years or so you'll get the membrane ripping, and then you need to replace the membrane. And here the pressure, the ultimate pressure is around 1 millibar that you can get to. Yeah, I should write that in a way that's maybe a bit easier to read. P is around 1 millibar. Okay. So the next one that we have is the rotary vane pump. And the rotary vane pump essentially works by having a drum with a slit, and you have some kind of vein, some veins coming out here, and eccentrically to it, and I should probably draw that afterwards. Eccentrically to it, you've got a chamber, and again you've got an inlet and an outlet. So we're going in here and we're going out here. Obviously this is the case if the whole thing spins this way. So that if you go in, the vane opens up, and if you go out, the vane closes. In order for that to work, we need the whole thing to work in oil. Okay. So we have oil in there. And the good thing about this system is these pumps is also they are very simple and cheap, and they're also relatively silent, and they have a good pressure. They have a good ultimate pressure. They need the oil needs changing. And the oil can, and I say will, contaminate UHV systems. So essentially, some of the oil will come out also through the inlet port eventually over time. Be it because you might have had a loss of electricity, and it just plops back, stuff like that. So essentially the oil will eventually go everywhere, but the pressure that you will get is around 10 to the minus 3 millibar. Okay, so you will get very good pressures with these, very good pressures for very little money. And another good thing is they can operate in dirty environments. I should leave that out for Adam Pro because it's not important for us. But also with the oil, you'll take any small debris or anything that's in there, which just goes into the oil, and you just need, if your system works a little bit dirty, you just take the dirt out with the oil essentially. But that's maybe not as important for us for Adam Pro tomography. But essentially the most important thing in this case is they can get you to very good pressures, but they will eventually contaminate your system. They will eventually contaminate your system, and this is why we don't find them that often. You can take some precautions like put in oil traps and the like, or on our field iron microscope we have a rotary vane pump where we have a very long hose and then we have a vacuum tank in between. So we've put in some effort to shield the rotary vane pump, or to shield the system from the rotary vane pump, not the other way around. But you have to decide whether that's worth it or not. Okay. The next type of pump that we have is a scroll pump, and a scroll pump, and I hope I can draw that properly. It's essentially a pump where you have an inner scroll. And counteracting to it. So you have one static scroll, and one dynamic scroll, and essentially the moving scroll rotates with a certain motion around the static scroll. And what will happen in this case is that we have an inlet here. Oh, sorry, I should probably use the same colors as above. So we have an inlet here, and we have an outlet here. And what would happen is that as the scroll moves, you know, we have air or whatever we have going into here, and then it gets compressed through those rotary motions, and eventually ends up in the middle. The good thing about those pumps is they are dry. Yeah, so usually those tips are made from PTFE, so you don't get the problem that you have any oil contaminating. So simple. I should put clean here as well. So they are dry. They are relatively silent, and they have a good pressure. They have very good pressure. Good pressure. So we usually end up at about 5 times pressure, about 5 times 10 to the minus 3 millibar. So a bit worse than on the rotary pumps, but still quite okay. The downside of those is they also need periodic maintenance. They're a little bit more expensive. So if this is, if this is dollar, this is dollar, then this is dollar. So price, I wouldn't say they're super expensive, but a little bit more expensive. And also they can wear faster without load. So the problem in this case is that you have some friction between the PTFE and the scroll. The scroll is usually aluminum or steel, and so you will get some wear. And if you always just pump very little vacuum, so if you, for example, backing an ultra high vacuum chamber, then the dust that comes from that friction will just stay in your pump, and it will increase the wear even more. And as a result, they do wear relatively fast if you don't have a lot of load. Yeah, so they have that problem. Even though we on our pumps we didn't. So if you get the good ones, then that problem is not super bad, but it's still there. Yeah. And this makes these systems very. This makes these pumps very good for example, if you want to have a system with only a load lock, because you periodically pump the load lock from ambient pressure, which clears out all the dust, and then you don't have too much of a problem. Yeah, so their scroll pumps are a pretty good choice. And as a last pumps, what we have are so-called roots pumps. So roots pumps are usually multi-stage pumps, but I'll just draw one stage. And they essentially work by having high precision, like dog bone shaped thingies in here. Oh, that should be ending up here. And so you've got an in and then out. In this case, on the basis that the rotational direction is this way. Yeah. And you usually have multiple stages, so that you have an entire row of these root cylinders, and they are all connected to each other, and so you get an entire cascade of roots pumps, getting you to a good vacuum. And about those, they have a good vacuum. So the pressure that you get is around, depending on which ones you get, it's around 10 to the minus 2 to 10 to the minus 3 millibar. So we have some pretty high end ones that can get you down to 10 to the minus 3 pretty well. They are very clean. They are maintenance free. And this is really what they've got going for them. So they're super clean, they have good vacuum, and they're more or less maintenance free. So you buy them, you put them in, and you don't have to worry about anything. And they have mainly two downsides, and the first downside is actually price. So they are definitely the most expensive part. They're definitely the most expensive pumps. And the other downside is they are loud. They are very, very, very loud. So if you need to put your backing pump in the same room as the rest of the system, then you're not going to be very happy with the roots pump. So I had one of my students use two roots pumps on an experimental setup that we were working on, and you could only literally sit there with earplugs and then like the Mickey Mouse earmuffs on top of the earplugs because it's loud. Yeah, they're pretty loud. But if you can separate them out, have a different room and put them into some acoustic enclosure, they will definitely serve you really, really well as backing pumps. But you'd have to spend they cost about 3 to 4 times as much as a membrane pump. So if you use turbo pumps, then modern turbo pumps very often have some compression stages that make it possible to use backing pumps that essentially membrane pumps as backing pumps, and you don't lose a lot of vacuum performance. So these days membrane pumps are not a bad choice. They're clean, they're simple, they're cheap, and it just every 2 years or so you just put a new membrane in. But these are the choices. We actually operate all of the different ones here for different purposes. Sometimes we've learned that our first choice was maybe not the best choice, yeah. But these are essentially your options as backing pumps. Good. But I don't think we're gonna. It doesn't make much sense to go through the individual pumping characteristics, and so let's go to the ultra high vacuum pumps. Yeah? And for the ultra high vacuum pumps, the probably in the future most important pump right now. Right now we're using a lot of other pumps as well, but in the future the most important pump and currently also a very important pump are turbomolecular pumps. Yeah? So turbomolecular pumps, and so essentially what a turbomolecular pump is in principle is that you give through adsorption, you give a molecule a speed in a certain direction. And I'll show you an actual pump in a second. But the actual shape of the pump might suggest that there's some fluid dynamics going on. It is not. Okay. So these pumps are fully kinetic, and if you look at the very, very early pumps, they actually they looked pretty funny. So the patent was from someone called Gade, Gade in 1913. And the first tour molecular pump is essentially literally just a spinning cylinder. So a cylinder that spins very, very fast. And you have an inlet and an outlet. And here just some kind of skimming device in between. And the rest is just literally in and out. And the thought behind that is that if I spin the cylinder fast enough and a molecule adsorbs here, goes around on the cylinder, and it happens to desorb here, then it will have a speed that makes it favorable. It makes it favorable for it to go out the outlet. And of course, these days we don't have spinning cylinder turbomolecular pumps anymore. But this is the basic principle, and this is why pressure in to pressure out equals e to the power of AV, and V is the blade velocity, or the absorption piece, whatever you want to call it, velocity. And A is a geometric factor. And A is a geometric factor, okay? And that's what I meant by a differential pump. So if we at a given pump operation, so the geometric factor is just a factor of what our pump looks like, and a given blade velocity, we have a ratio between pressure in and pressure out. And this is very important. The pressure out to pressure in is e to the power of minus AV. You could just swap it around as well. And this is why it's very important that it spins very, very fast as we can make anything spin. And that we have good backing pressure as well. Okay? Of course, for a modern turbomolecular pump, and maybe let me just, just want to move this. Why is it not let me? Okay, so for a modern turbomolecular pump, TMP stands for turbomolecular pump. We've got the combination of rotors and stators. Yeah, so we essentially have blades that go this way, and we have blades that go the other way, and they sit on some rotating device. On the rotor, obviously, we have a velocity V, and we have an in, and we have an out. And the purpose of the whole setup is that if you let me just draw that separately. If we look at the if we look at the if we look at an atom adsorbing at the surface here, so a molecule comes in and adsorbs here, right? Then the question is, what is the probability for it to go in this direction? Because we want to maximize the probability, essentially. So maximize probability for molecule to go this way. Yeah. And so if from the inlet side, if a molecule comes from inlet side, and I'll just oh come on, there must be a way to elegantly select. No, that's already the move command. What happened to my selection? I went to the wrong selection tool. My bad. So let's just move this thing over here, and let's move this thing over here, so I've got a little bit more space to draw for you. And so essentially, if I look at the blade itself, or just a space between two blades, and I get a molecule from the incident side. Yeah, so you get a molecule absorbing here. Then the question is, and now we're looking at it from the perspective of moving blade. Yeah. So from the perspective of the moving blade, then we would have, should draw it a little bit. Yeah, I'll use color again. It's easier. So from the perspective of the moving blade, essentially we have an angle. We have an angle phi 1. We have an angle phi 2, and we have an angle phi 3. So if the molecule absorbs, now maybe use some color here as well, so that this is the incident velocity vector. So that if our molecule moves, if our molecule desorbs, and it desorbs in the direction of phi 3, then it has moved to the right. If it desorbs in the direction of phi 1, then it will desorb and move to the left again. And if it desorbs in the direction of phi 2, then it will desorb onto the other side of the blade. And so the faster the molecule moves, the faster the blade moves, the higher the probability that the molecule will desorb in the direction of phi 3. Yeah? And this is essentially the way to get them to move to the right. And if you do an entire balance, so this is for incident side, okay, so this is for the incident side. And if we draw the same thing for the, let's just make the blades a little bit thicker. Yeah. And if we draw the same thing for the molecules from the right side, then you know it would be coming from here, and we would have a phi 1 in this direction, then in this sort of order of magnitude, phi 2 in this direction, and essentially a relatively small angle. Of course, if the blades are together a little bit further together, then those angles change, and a phi 3 this way. And essentially, so our atom absorbs here, then sits here, and then can leave the blade. So the blade spins with the velocity v, and maybe I'll just note that down here. So we've got the velocity v here, and we've got the same velocity v here. And so what we need is essentially for it to spin fast enough that the desorption is much more likely in the right direction than into the left direction. In the coordinates in the global coordinate system, because this is now in the coordinate system of the blade. And this, essentially this, the ratio between the area going to the between the solid angle going to the right here and the angle going between the angle of that opens up our molecule going to the right and the angle that opens up our molecule going to the left, that ratio is essentially our compression ratio. And this is what we see up here. This obviously just applies if we only have absorption based pumping action. Modern turbomolecular pumps usually have a combination of one or two stages that can also do fluid dynamics, so that you can use cheaper pumps and get to still pretty good pressures. In turbomolecular pumps these days, the pressure, I don't know, I should use some different color maybe for that. Maybe the dark blue, I like the dark blue. The pressure, the ultimate pressure. So at some point, of course, the pressure is no longer going to be limited by the backing pressure, but by people do turbos backed by turbos and get to pretty good pressure, so to an extent it is, but the manufacturers, they give you an ultimate pressure, and the ultimate pressure is usually around 5 times 10 to the minus 10, and if you remember right, that's good enough for atom probe tomography. And these days you can get some that can go down to less than 1 times 10 to the minus 10. I have one system that we operate that goes into the higher 10 to the minus 11s just with a turbo pump. Yeah? So that's all doable these days, and that's why I think turbo pumps are going to be the future for atom probe tomography, just simply because they have upsides. They can go from ambient to UHV. They are gas agnostic largely, so obviously this is a momentum calculation, so the higher the momentum is of the particle, the better it gets pumped, so heavier gases work better than lighter gases. They're just pretty simple in operation. The downside is that they are sensitive to pressure increases. So if you suddenly put a lot of gas into your system, your turbo pump might not like that, and that is because it spins very fast. So if you suddenly get pressure in, the bearings might start seizing up. Modern pumps can take that a couple of times. Older pumps were really bad at taking that. Some of our pumps have already taken a little bit of a beating there, and maybe I should have put that on a different. Let's put that on a. Let's put that on a different slide, maybe. Because there is a lot more to be said about these pumps. So turbo molecular pumps, and so you can get them from about 80 liters per second pumping up to about I mean, realistically, you can get some very, very large ones with a couple of thousand, but for us, really relevant in the size of flanges we use up to around 1,000 liters per second and above. And of course the flanges then get a little bit larger. So the larger the flanges, the smaller the rotational speed, just because of centrifugal forces. So here we typically have 1500 hertz rotational speed, and here for the larger ones we might have 500 to 1000 hertz. So this would be 90,000 RPM. So spins very, very fast. I think a Formula 1 car spins at 10,000 RPM or 20,000 RPM. We're spinning at 90,000, so that's more like dentist drill kind of level. And because of that, we have the fact that they are sensitive to pressure shocks, and that they are also sensitive to vibrations. I don't know that for a fact, but I've heard that, for example, people in Japan don't like to use turbo pumps because if you get an earthquake, you might have a problem with it. There are other stories that I have confirmed. For example, some colleagues of ours in a different lab that I'm not gonna name, they once had a system with a turbo pump mounted on an optical table, and someone just hit his fist on the table, and the whole thing blew up. So yeah, that's not very good, but they can give you good ultimate pressure. For a wide range of gases. Then the gases are removed, which is in contrast to the other pumps we're going to look at. So if you, for example, have process gases that you want to get in, then it's easy to remove the gases. For example, for a field ion microscope, it's, for example, you can even do things like have an equilibrium between gas coming in and gas being pumped out, which makes it very easy to adjust the pressure, things like that. So turbomolecular pumps are actually very great for the kind of work that we do. The other thing about it is they're very clean. So we have no ionization. The other pumps, some of the other pumps that you will see, ionization, ion getter pumps, they can lead to ionization. So if you have some contaminants that you know, if they're just there, they're not a problem, but once you ionize them, they become a problem, like hydrocarbons, then you're not going to have a problem with a turbomolecular pump. Good, and so with that, actually, let me show you a turbomolecular pump. I brought an older one here. So a big thank you for the turbomolecular pump to our colleagues in Sweden. I actually got the turbomolecular pump from the group at Chalmers. It was on their old focused ion beam system. So it does have an ISO-K flange instead of a CF flange. Obviously, if you want to have a UHV system, you want to have an ISO-CF flange. And what you can already see here is that usually we have some kind of, or we can have some kind of inlet protection, so that if we have something falling on a turbo pump, it doesn't get into the pump. And then we have the pump itself, so you can see it's rotating. That pump, the bearings definitely changing. So you can see this should, if this thing would right now spin at a kilohertz, which it probably should, I don't think the bearings would survive that. But anyway, so this is the sort of spinning you would get, and you can see you've got rotors and rotor blades and stator blades, and then usually or very often for protection you put some grid like that on. So if you get to design a UHV system, it's always good then to mount your turbomolecular pump in a way that you don't need that thing here, you don't need that inlet mesh, because of course it leads to a reduction in the pumping efficiency, because any molecule that hits the mesh will go the other way out again. So essentially the area loss that you have here is essentially a loss in pumping speed. But if it's mounted, for example, at the bottom, then there's not much you can do about it. You essentially have to use one of those meshes. Otherwise, if someone drops something like something in here, a sample or something, it will just blow the pump up. This pump, then you can see here, you've got an outlet, and on the side, so you can see here, you've got an outlet. So this is where you would put the backing pump, and here you've got a second thing that looks like an outlet but isn't actually one. What that thing is a venting valve. So if you want to run down a turbo pump, it can take quite a while until the turbo pump actually spins down. So if you have a good vacuum and you just let it spin down, it might take something like 15 minutes, which if you're operating an SEM or an atom probe with a load lock, you don't want to wait for 15 minutes every single time you want to open the load lock. And so you want to have the ability to put a little bit of gas into a turbo pump just to slow it down quicker. Obviously, don't put too much in, otherwise you'll blow up your turbo pump. But if you get one of the approved valves from your turbo pump manufacturer, it will have the right amount of gas flow coming through it, so that you don't have that problem. Which leads me to actually one last problem that I've forgotten to mention, and that is that turbo pumps can also cause vibrations. So if you have a system like an atom probe with a very small spot size, laser spot size, for example, and it can't have a lot of vibrations, then turbo pumps can cause problems. But modern turbo pumps with magnetically levitated turbo pumps or hybrid bearing turbo pumps have very, very small amounts of residual vibrations. And for electron microscopy, you can even get special turbo pumps with extra low levels of vibration. Good. So much for turbo pumps. I hope you like turbo pumps now. I certainly do like turbo pumps. And if I would build a general purpose run-of-the-mill atom probe system right now, it would just be a turbo pump system. Anything else would just be the extra effort doesn't really stand for it anymore. and you avoid a lot of other problems with that. It's not going to be as super clean as some of the other approaches that you can take with sorption pumps, but you can combine them with sorption pumps. For example, you can use a non-evaporative getter pump together with a turbomolecular pump, which can be very effective. And so you can do some pump combinations there as well. Especially because non-evaporative getter pumps are very good at pumping hydrogen, which turbomolecular pumps, because they're essentially momentum pumps, and so hydrogen molecule is not going to have a lot of momentum. They're not very good at it, and you can combine it with a non-evaporative getter pump and get a pretty good system. I think actually the Inspico systems that came out of the Stuttgart group, they use a combination of non-evaporative getter pumps and turbo pumps, which I think is for a general purpose atom probe is probably what I would do right now as well. It's a pretty good choice. Anyway, so much for turbomolecular pumps. So let's move on to sorption pumps. And for sorption pumps, I'll just start with pumps that I haven't seen used much in atom probe tomography, but that might be interesting. For us as well at some point, and that is the use of cryopumps. Yeah. And let me just open a new slide. And so let us just look at. Oh, that's the wrong direction. Let us just look at cryopumps. Yeah. At cryopumps, and cryopumps are actually relatively simple pumps. So usually you have a Gifford-McMahon cryohead, and we'll get to what that is in a bit. A two-stage Gifford-McMahon cryohead, and actually most GM cryoheads are specifically made for that purpose. Yeah. So if we buy a GM cryohead for our atom probe to cool our sample, it's actually one that was more or less designed for cryopumps for the electronics industry, and we're just using it. We're just diverting some of those into our hands. And so essentially what it is this here is a GM cryo, and you will learn about what that is in later part of the lecture. So you'll have a GM cryo, and the GM cryo has two stages. And again, we'll get to why and what and so on at a later point. And you'll have a stage 1, which will be at about liquid nitrogen temperatures. Yeah, let's say about 80 Kelvin. Yeah. And then you will have a second stage, and the second stage, these belong together, and this here is going to be about, depending on how large it is, but let's say about 10 to 20 Kelvin. And what would happen is that you get just by temperature. I've drawn the whole thing. I've drawn the whole thing before. So just like in the last lecture, just by temperature you will get sorption of molecules onto especially the colder part. So you get some sorption of mostly, water that also already sticks at 80 Kelvin, and things like nitrogen, argon, CO, CH4, and so on, that will stick on the inner part here. But what is important here is that usually we also have activated carbon. Yeah, so we usually also have activated carbon. And the activated carbon especially absorbs hydrogen for hydrogen absorption at low temperatures. And so because you can see all of the other gases would be pretty easy here, but only hydrogen would be left. So if we look at equilibrium pressure, so P equilibrium versus hydrogen adsorbed or sorbed, then you'll see that and we have that in standard cubic centimeters, so cubic centimeter of hydrogen at room temperature per gram of activated carbon. And the limit will be at about, 1 gram of carbon will be able to take up about 400 standard cubic centimeters per gram. So that's quite a lot. And depending on what kind of temperature you have, you will get different equilibrium pressures. So, for example, if we're at 10 Kelvin, at 10 Kelvin versus 15 Kelvin versus 30 Kelvin, we'll get different equilibrium curves. And the important thing about that is that they can be at very, very low equilibrium pressures. So we're talking, this might be 10 to the minus 4, 10 to the minus 4 millibar. Millibar. So this might be 10 to the minus 4. No, this already, what is 30 Kelvin? This is more like 10 to the minus 8 already. At 15 Kelvin, we're gonna be at, let's say, if this is 100 SCC, then at 15 Kelvin and 100 SCC, we would be at 10 to the minus 12, and so on. And then we'll get to some pretty ridiculously low, pressures. And essentially what that means is that if we have not too much hydrogen ingress and we're at a low temperature, then these cryopumps can give us a really, really good pumping action also for hydrogen through the activated carbon. So the question is then, if we have, for example, an atom probe that is voltage only, so we don't. So if we have an atom probe that is voltage only, for example, why do we not use that? Or if it's a laser atom, I've forgotten to mention maybe GM cryo. The problem is that GM cryo causes vibrations. It's kind of like if you go into the atom probe room, and you always hear the that's the GM cryo. And here we've just used the GM cryo for cooling, for pumping. And we have the same problem as always with the GM cryo. It will create some vibrations. So this is why we haven't used in atom probe, we haven't used cryopumps as much as we could. But if you build a system that's voltage only, cryopumps are actually a fairly decent option. And I believe the guys in Rouen in France, they have used or are using cryopumps in their systems. Okay, so much for cryopumps. The next ones that are important for us are actually sublimation and getter pumps. And The most important thing about sublimation and getter pumps is that, so if we have sublimation and getter pumps, then we're using the principle is physisorption, okay? Sorry, chemisorption. So essentially that we have a surface that we provide that our molecule chemically bonds with. And if you for example look at oxygen on metal, on general metal surfaces, just like a steel surface or something like that, will have 12 to 17 kilojoules per mole. And if you remember before, sort of our bad area is about 100 kilojoules per mole, so this is something we can get rid of pretty easily. Oxygen on blank titanium will have around 1,000 kilojoules per mole. So essentially that thing is never going to come off. Huh? And if you remember before, then at room temperature, when we had our absorption curves, then it will never come off barrier was roughly around 200 kilojoules per mole. So 1,000 kilojoules per mole just means this thing is never going to come off. Huh? And essentially the sticking time that you have of a molecule on a reactive surface is some kind of tau 0 times exponent of the delta E, the desorption energy, to RT. And so if we have a very high delta E to RT, then essentially a sticking time goes up and goes towards forever. We can do a calculation on that, but essentially it just means it doesn't ever come off ever again. And so the question is now, what kind of mechanisms can we use to provide some kind of surface like that? And essentially we have two ways of doing that. Or two ways of doing that by just using sorption. Okay, we'll come to ion getter pumps where we're using sorption and implantation together. But for now, in this case, we're going to be using either a titanium sublimation pump, or we're using a non-evaporative getter pump. Okay, and a titanium sublimation pump is actually fairly simple. So you have some kind of cylinder where you have a titanium filament, and you heat up the titanium filament. Yeah, so you have some kind of current I going through for resistive heating, and then you heat it up to a to pretty nice red glow, or your red yellowish glow. Yeah. And what happens is that you get, and for titanium I should probably use some nice titanium gray. So you'll get titanium sublimating on the surface here. Very simple principle, and very easy to do. And that sublimated titanium will then offer offer a surface to react for any reactive atoms. So you can already get from the principle here maybe that it's chemical absorption, that if you have something like argon, if you have some noble gases, they are probably not going to stick at all. Which can be an upside, by the way. So if you want to do field ion microscopy, it's really great to use those pumps because they will take any reactive gases out of your film gas. You might have some residual hydrogen, you might have some residual oxygen or whatever in there, and it will just take it out, and you will be left with a very, very pure, very pure film gas. Okay, so you get some titanium sublimation here. And non-evaporative getter pumps work a little bit differently. So with a non-evaporative getter pump, what you have is you have some kind of sintered metal. Yeah. So if you heat titanium to a high enough temperature, it will dissolve its own surface oxide. Yeah. And so for a temperature for pure titanium, it's about 450 degrees, but you can find some alloys, titanium zirconium aluminum. They're very special alloys that if you heat them if you heat them high enough, what will happen is they will just and I should just make some kind of oops, no, that's not the way it looks like on this side. Yeah. So you might have some surface oxide. What color are we going to use? You might have some surface oxide. Yeah. And if you raise the temperature, if you have this surface oxide, let's just make a surface with an oxide. And you are at room temperature. And if you go to raise the temperature to, say, depends on the alloy, but it can be as low as 150 degrees. But let's say somewhere between 250 and 450 degrees. What will happen is that the oxygen will just be dissolved and you have a blank metal surface. And you do that with a sintered material. So that you have a lot of surface. Which means that you can only do that for a certain amount of time. So they're not really great to pump a lot of gas, but they're really good at low pressures because the surface is always going to stay the same, and if you don't need to absorb a lot, that's great. And they have the additional upside that once it's blank, or at let's say it's 450 degrees C, so the oxygen goes in. The oxygen goes in. And any hydrogen that we used to have, sorbed, the hydrogen goes out. Yeah. So the hydrogen sorption is actually reversible. So you can get rid of the hydrogen because of its high diffusion coefficient. So anywhere where you can get rid of hydrogen, anywhere where you want to get rid of hydrogen, non-evaporative getter pumps are really great because during your bake out, you can run a bake of the non-evaporative getter pump, get rid of all the hydrogen, create a blank surface, and then start sorbing again. And that sorption actually of the oxide, you can do that quite a lot of times, but probably about 100 times. So for ultra vacuum systems that they don't open up all that much, it's actually pretty okay to use non-evaporative getter pumps, and you will never get to a level where you have so much oxygen in your non-evaporative getter pump that it will become a problem. But of course, the sorption capacity of those pumps is limited, because you create a surface, and once that surface is fully sorbed, it will no longer sorb. So if you have a lot of hydrogen in your system, you probably need to regenerate your pump if you've got a non-evaporative getter pump. For a titanium sublimation pump, because it's only one flat layer of titanium, you will just need to run the filament again at the pressures that we are working at, probably every week or every 2 weeks or something like that. For a neck pump, you usually need to do a regeneration every time you open the system. So I haven't done one ever since I've closed up my atom prop that runs on neck pumps. The difference between those in terms of practicality is here we've got the plus is good hydrogen sorption, very high pumping speed. So essentially, if you put a cryo shield on there, you will get dendritic growth of the titanium, and you will get very, very high surface area, and you will get up to 10,000 liters a second hydrogen pumping speed. Very, very high pumping speed. The minus is that you need to regenerate the titanium layer, and this means you produce heat. Yeah, because you've got a hot filament here at the bottom, which means you produce heat that you put into your system. With a non-evaporative getter pump, you also have good sorption, good pumping speed, and the minus here is price. So I've bought two pretty big ones, and it cost a lot. So I think I paid about 10,000 euros per pump for a 1,000 liter a second pump. But once you have them in there, the good thing is they just do the pumping action. They don't need any power. So even if you have a power outage, it will just keep pumping because it's just a blank metal surface. And they don't produce any heat ingress. They don't produce any vibrations. They're just there. They're just doing their thing. So as long as you don't have a big amount of stuff to pump, they do an extremely good job. What I do not pump, of course, is noble gases. Just like the titanium sublimation pumps, none of the getter pumps are particularly good at that, and especially the sorption pumps do not pump anything that doesn't react. So if you have something that needs to be pumped that is non-reactive, you probably need something else in there. For us in Atom Probe, it's not as critical because we have our cryo head, and the cryo head is actually a pretty good pump for anything that is not reactive and is not helium. So the only thing you're left with is helium, and you don't get a lot of helium ingress. Helium doesn't just kind of randomly come from somewhere. Good, and as the last set of pumps that we have for atom probe tomography, I'll go through ion getter pumps. Or IGPs. So we'll actually get to something very, very similar when you look at pressure measurement. And the truth here is ion getter pumps actually came from pressure measurements. In the 60s, when people started having ionization gauges, they tried to test them by themselves and see if there is any drift. And really looked like the ionization gauges always were drifting to better vacuum. Until people found out, no, they're actually acting as pumps. And so they just built big versions of them optimized for pumping, and that's what an ion getter pump is. And so essentially what we have here is we have an anode and a cathode. So we have a system where we do two things. First of all, we ionize any gas that goes into our system, or we ionize part of the gas that goes into our system really, into the pump, and use that ionized gas to sputter titanium or titanium tantalum combinations, some reactive metal, usually it's titanium, but it might not be pure titanium. And that gives us chemisorption. So we combine the action of what we had with the titanium sublimation pumps and with the non-evaporative getter pumps with a method to essentially bury also non-reactive ions, non-reactive elements. And the way the whole thing works is that we have an anode and a cathode. So we have essentially have an anode cylinder. So that's look in 3D, it's a cylinder. And then we have cathode plates here. So we have cathode plates here. And we apply a high voltage. Lot of high voltage. Typically, I don't know, 5 to 10 kV, so pretty high voltage. And we also add a magnetic field B here. So we might have some big magnets, going around the whole thing here. And the reason for that is that if we have that, we actually ionize. If we have an ionization event, so let's make the molecule a different color again. A molecule will be green again. So our molecule will go in, and we'll get into the anode cathode plate area, and essentially will be ionized. So you'll get a plus charge and we'll get an electron. And what will happen to the electron is that it will actually move through the magnetic field in a spiral way, right? And that's what we have the magnetic field for, so that we have a relatively high probability that the electron will then hit another molecule and ionize that other molecule. While the anion then hits the negatively charged plate, and there causes sputtering. So causes sputtering. And so we've done two things. First of all, if this was, for example, something that wouldn't stick on blank titanium like helium or argon or something like that, then we might have implanted that. And the sputtered titanium will create fresh surface. So we'll have some surface coating here. Obviously, we'll have a little bit of a deeper groove here, and most of the titanium will be here on the sides. But it will coat essentially everywhere. It will also create, little wires here, little nanowires that grow here. So I need to regenerate it sometimes so I don't get discharges in there. But essentially, this is how an ion getter pump works. And the good thing about this is it pumps non-reactive. It pumps pumps reactive and noble gases. and noble gases. Even though the noble gases, it's not great at pumping noble gases. So a turbomolecular pump is much better at pumping noble gases, but it's okay. It does pump noble gases, and you can get special ion getter pumps that are made for that. The other good thing is you can get a very high bakeout temperature. So essentially, if you remove the magnets, so the magnets usually only survive about 220 degrees or something, and then they get demagnetized, which would be a problem. But if you remove the magnets, you can do 450 degree C bakes without the magnets. So you can bake very high, so they're very clean. They have a very good ultimate pressure. They've got a very good ultimate pressure, so usually less than 1 times 10 to the minus 11 millibar. So this is actually the reason why they are used a lot in atom probe tomography. But they also have some downsides, and the two main downsides is the first one is ion re-emission. So not every ion that's in there gets trapped in there. So some ions make it back out, and they then float around in your system. And the problem for atom probe is in this case that they will get caught by your detector, because the detector has a front potential that's not at 0 usually. So it just catches those ions, and you will get those ions as noise on your detector. So in the LEAP, for example, or also in the Oxford atom probes, what they did was put a lot of shielding around the detector so that ions from the IGP can't go back into the detector. But that obviously makes your system a whole lot more complex than probably today it needs to be. And also it means in your detector area you don't have as good a vacuum because you've got shielding in there. So this is a little bit limiting. Plus, you need to have the shielding attached somewhere. You need to have the sample attached somewhere, and so on and so forth. And the other downside that they have is maybe to give you an idea of how much we're talking about here. So I on our home built atom probe, on the voltage pulsed home built atom probe, we have a very tiny ion getter pump to get rid of noble gases if we do FIM, which I've never done, so I'll take it off. This doesn't need to be there in the end. And that IGP, if I switch it on, so that's an IGP that's about the size of a fist. If I switch it on, it causes about 6,000 counts per second on the detector. So it's bad. It's really bad. And the other downside is, and that's for if, so they can be very heavy. So they can be very heavy. So if you have a 500 liter per second pump, that pump has about 100 kilograms, right? And this might not sound like a big deal, but this is really determining how you design your system. And if you look at the Oxford Nanoscience systems, the Chemica systems, Chemica Imago systems, and other systems that work on a basis of ion getter pumps, the ion getter pump always needs to be mounted at the bottom, because you can't mount it on the side. The whole thing's, you're never going to be able to properly work with that because it's so side heavy or top heavy or whatever. That makes it really hard to work with it, and you need to design your system essentially around that extremely heavy pump. And this is actually the biggest problem I see with ion getter pumps. Everything else, your ion re-emission, can be dealt with. but in the end they are extremely heavy. Of course, you have the upside that you can bake at a very high temperature, they're very clean, they can get you to extremely good pressures, but it makes your system somewhat unflexible. In some other chambers, for example, in Rouen, where people use just turbo pumps, or the guys in Stuttgart that just use turbo pumps, you can just put the sample on an optical. You can just put the system on an optical table, or you can put it on wherever. It's just very easy to mount because apart from the IGP, the system maybe weighs 40-50 kilograms, not a lot. If you put an IGP in, it will weigh a lot more, and you will essentially set your system to a certain layout. And that is to an extent problematic if you want to do laser experiments, because it would be nice to get the laser either in through the bottom or out through the bottom, or do some, not block an entire side of the atom probe just with the pump that you're always set to. But they are state of the art, and they are used a lot, and if used properly, they do an extremely good job. Good, and with that, we're actually finished with the section on pumping. Obviously, there are some more pumps out there, some more obscure ones that we are not using in atom probe tomography that don't make that much sense. And obviously, there's a lot more depth to pumping and getting a good ultra high vacuum than I was talking about here. But I've already been talking on this section for an hour and a half. So yeah, if you're really interested in building your own system, you would probably dig a little bit deeper into the whole topic than I did right now. But the general vibe right now is that you use either an ion getter pump or an ion getter pump in combination with a titanium sublimation pump. You can actually buy them as a package. Or you use an ion getter pump together with a non-evaporative getter pump, or a non-evaporative getter pump with a turbo pump. And these are sort of the standard setups, and I've gone through the upsides and downsides of each of the setups. And yeah, you will, for your experiment, obviously you can choose what you like. I think a good turbo pump these days, maybe with a small non-evaporative getter pump, is a very, very good package for atom probe tomography. Ion getter pumps, especially together with titanium sublimation pumps, are also an extremely good package if you take care of the ion re-emission problem, and if you're willing to design your system around some very, very heavy pump. Okay, with that, I'll end that section, and we'll then move on to, in the next session, we'll move on to vacuum measurement, where we'll look at rough vacuum measurement and high vacuum measurement.